Assalamu alaikum everyone. So today we will be having lecture number 26 and we will be discussing about finite state machine design procedures, right? And these are the bullets which we will be going through one by one, right? What we need in order to design a system that constitute flip-flops and combinational logic, right? The requirement, right? I mean, we have to specify, or we must specify the system accurately, right? And then from the specification we move on to the state table, right? From specification, what we mean what are the inputs, what are the outputs, right? And what will be the states that are being included or that the system have to go through, right? So after all sort of specifications, we will move towards the state table, right? And the state table includes current state and the input and the next state and the output, right? And obviously we have to fill the state table on the basis of the current state and the input, and we will be filling the next state and the output column, right? Ultimately what we need to do, we need to draw the circuitry or circuit diagram, right? So these are the bullets or main points which we will be discussing in today's lecture, right? So let's start. Whenever we talk about a state machine, right? So an idea comes to mind that how it fits into the computer hardware, right? So let me define the computer hardware, right? Actually, whenever you think about the computer, we need two main entities. First is the data path, right? And second is the control. Or in other words, you can say that we need data, and in order to handle or manipulate that data, we need some sort of instructions. Obviously, you need to transfer data from one part of the unit to another part, right? Within the computer system, right? So there are a lot of different modules, units that are being involved within that computer system, so we need those sort of different entities, right? So data, its transmission, and the instructions. On the basis of those instructions, we have to manipulate that data, or we can handle that data in an effective and efficient way, right? So when we talk about the data path, right, so that includes registers, right? You can say we can also have the combinational circuitry at the input of those registers, right? As we have seen in our previous lectures, that those flip-flops or registers that store the data or states, they are being provided the input by the combinational logic or combinational circuitry, right? So you can take the example, or you can think about the buses, right, or which you have to transmit the data, or they are connected. So a lot of different units, they are being connected parallelly to those buses. So whenever a unit want to take the control, it has to send some instruction or control information that it is going to send the data, right? So now the control is with me, right? So that is the sort of situation, right, which we have to handle. On the other side, when we talk about the control, so that includes the finite state machine sequences, right? Or you can say it signals, right? Control signals. That includes the instructions for the data paths, that what they have to do next, right? So these are the instructions to the data paths, right? For example, it can be an instruction for the bus, or it can be an instruction for the ALU, arithmetic logic unit. Let me give you an example of the addition which we have gone through. For example, we have to add two 4-bit binary numbers, right? So addition is an operation, so we need a lot of different instructions, right? So first we have to load those two numbers, right, to a particular location or particular circuitry so that we can add them, right? So after that, so for that we need to send some instructions to some bus, right? And so that for example we have two numbers A and B, so first we will load the number A in one register, and then we load the number B in another register, right? So this is also being done by sending certain instructions to the bus, right? So, and then after that what we need to do, we need to instruct the control unit that now the numbers are being loaded and we have to add the numbers. We have to start the operation, right? So we will send an instruction to the ALU, right, and it will start an addition process or addition operation, right? So this is the sort of hardware, right? Computer hardware or computer system, right? So if we talk about in more details, right? So we have two parts in our logic, right? First is the combinational logic and the second is the sequential logic, right? So we know that in combinational logic we have the inputs and we will be keep on getting the output as long as the inputs are present, right, at any point in time, right? So there is no clock involved, right? So there is no memory involved, right? So you can only say that whenever we have the input, our circuitry, combinational circuitry will function, and we will be getting the output. As long as the input will be removed, we don't have any output, right? So there is no storage element involved within the combinational logic, right? So but on the other side, if I draw that combinational circuitry along with some feedback loops, right? So you can see here a lot of different feedback, right? So these are different feedback loops, right? So what I'm doing, I'm dividing this circuitry into a combinational logic and the state logic, or you can say the sequential logic, right? So you can see that we have different boxes, right? So these are the storage elements and they are actually being used in order to store the states, right? So these are the feedbacks, right? So we have the feedback from the combinational logic, right? And actually we are storing different states, right? So that is the main difference. So here we have the storage, right? And we can store states, different states, so the memory elements are involved, right? So we need to decide when we have to store the state and whenever we have to provide the stored data as an input to the combinational logic, right? So these are very key and important elements, right? So that is the difference between the combinational logic and the sequential logic, right? So regarding the finite state machines, right? So actually here we are storing different states, and that's those states are being stored by using flip-flops, right? So we have to decide when we have to store those states, and then those when those storage elements has to provide the data as an input to the combinational circuitry, right? So let's start the design of finite state machines, right? So as we have mentioned that first very key point or very key element is the specification of the system in a clear way, right? So we have to specify the problem, what are the inputs, what are the outputs, what how many number of states the system can have, right? So let's talk about the example. We have to construct a system or circuit that can detect 3 consecutive ones, right? So the system should be able to detect 3 consecutive ones, right? So what we need to do, we need to define the states, right? How many states the system can have. Then obviously we have to map those states onto the binary values, right? Because we are designing the binary system, right? That is base 2 or binary system, so we have to assign the binary values to those different states, right? Then we will construct the state table that includes the present state, right, the input, and on the basis of those 2 different columns we will fill the next state and the output column, right? So this bullet is very important, right? So as I have mentioned that we have the combinational circuitry, right, and the sequential logic. So both logics are involved while we are designing finite state machines, right? So here what we need to do, because we can simplify the combinational logic, right? So it will be beneficial for us if we are able to simplify the combinational circuitry, which is providing the input to the storage elements, or which is also acting onto the front, or you can say which is at the output of the whole circuitry, right? So we need to use some mechanism. So here we have mentioned that we will be using K-map in order to simplify the combinational logic, right? And then we have to create or construct the circuit, right? Ultimately, or this is the final stage, that we have to construct the circuit. And we can also add some extra bullet over here that we can apply different values and we can verify either our circuitry is working properly or not, right? So you can also have the verification over here, right? So this is the example, same example. So here we have to define states, how many number of states we can have. So here I've mentioned state 0, right? So you can see there is no one, still no one has been detected, right? So we are sitting at S0, right? And if we have 0 as an input, right, so we will come back to the same state, right, and we are having no one, right, till at S0, right? So if you can see we have 1 as an input, right? So we will make a transition from S0 to S1, right? So you can see here state S1, 1 is detected, right? And here if we have 0 again as an input, so it means we will have to move back to the S0, and here again we have the same situation that no one has been occurred, right? So from if I am here at S1, right, so we have to remember that till now we have 1, right? So whenever we have 1 as an input at this state, so it means we have to make a transition from S1 to S0, right? So you can see that we have 2 1s, right? So at S2, state S2, 2 1s are detected, right? And from here you can see that we have if 0 is applied, so we will move back to the S0, right? If 1 is applied, then we have a transition for S3, right? So for at S3, 3 1s are detected, so that's it, and that will finish the job, right? So because we have to define or design a circuit that is able to detect 3 consecutive ones, right? So here are some of very important points that has to be noted, right? So you can see that we have 2 output arrows from each state, right? So this is one arrow for S0 and this is the second. if I talk about S1, so you can see that we have this arrow, right, and we have this arrow, so it's 2 arrows for each state, right? And because this is very simple, that we have 4 different states. If I count, so 1, 2, 3, 4, so how many bits are needed or are required in order to map those states? Obviously 2 bits. We need 2 bits in order to map or encode those states, right? So this is the, and then the next step, we have to define the state table, right? So here we have to define the state table, right? And you can see that in the state table, this is the column for present state, right? If I go back, so this is the column for present state, right? If I'm sitting at S0, right, and then there should be an input so that we can make a transition from one state to another state, or we have to in this case, if I provide 0, I will be at the same state, right? So we need an input. Then there is another column, next state, and the output, right? So you can see that we have different combinations for present state. These are 4 for S0, 0, 0, for S1, 0, 1, for S2, 1, 0, and for S3, this is 1, 1, right? So 0, 0, and input, because this is a single bit, so it can be 0 and it can be 1, right? Similarly 0, 1, for 0, 1 we can have input 0, and for 0, 1 we can have the input 1, right? 1, 0. So you can say that you can join or combine, right? So we can have a very simple state table where we can have x is equal to 0 and x is equal to 1, right? Or that has to be simplified. But here you can see we have 4 combinations, right? For A and B, 0, 0, 0, 1, 1, 0, and 1, 1, right? And they are being written over here for x is equal to 0, and the same combination for x is equal to 1, right? So same is the case with the next state. So ultimately we have to fill the next state table, right? So whenever we have 0, 0, right, and input is 0, we will be sitting at the same state, right? So whenever we have 0, 0 and input is 1, we have to make a transition from 0, 0 to 0, 1. So you can see whenever input is 1, we have to make a transition from S0 to S1. So as we have mapped or encoded S1 with 0, 1, so we have to mention over here 0, 1, right? And obviously we have to calculate or compute the output, right? So whenever we are sitting at 0, 1, that is S1, and input is 0, right? So we have to move back to the S0, right? So you can go back. So whenever we have input 0 and we are here at S1, so we have to move back to the S0, right? And whenever we are at S1, right, 0, 1, and the input is 1, then we have to move, or we will move to the next, right, next state, right, from S1 to S2, right? So that is the, and then same is the case for 1, 0, right? So now we are here at 1, 0, right, and 1, 0 is the S2, right? So if we are at 1, 0, right, that is S2, and we have applied 1, then we have to move to the 1, 1. So this is a transition. This is the present state and this is next state, right? So all you need is the state diagram, right? So, and then obviously we can calculate the output column, right? So here you can see we have encoded different states, right? Okay, so next step is also an important element, right? So that is the simplification, right? So here we have the table, state table, having all the values. So these are the inputs, right? And this is the output. So if I take those values all together, right? So 0, 0, 0. So you can remember, or you can have an illusion of the normal binary counting, starting from 0, 0, 0, 0, 0, 1, this is 1, and this is 2, 3, 4, 5, 6, and 7, right? So we have 3 different variables right over here, and for those variables we can have 8 different combinations starting from 0 till 7, right? So these are the outputs, right? So what we need to do, we need to compute the minterms for those different values, right? So this is the next state, right? So for A, I need to calculate the minterms, right? So you can see that here we have 1, right? So what I will be doing, or writing down the, right? So let's start. So this is M0, right? M1, this is M2, M3, M4, M5, M6, and this is M7, right? So, and if I write over here M0, M1, M2, M3, because we have to take a jump, and here M4, and here we have M5, M6, and M7, right? So what we need to do, we need to plot, right, for A. So this is the K-map plotting for A, right? So you can see we have M3, 1, right? And then M5, where is M5? M5, 1, right? And M7, 1, right? So we have 3 ones, right? And after the K-map plotting or mapping, what we need to do next, we need to look for pairs, right? So here we are looking for pairs, right? So you can see that we have this is the first pair and this is the second pair. So as a result of this pair, we will be getting the expressions, right? So we have AX, BX, right? And similarly, we can do the same job for B, right? So for B, we have M1. So this is M1. So let me write down, right? So we have M0, we have M1, and then M2. This is M3, and here we have M4, M5, M6, and this is M7, right? So what we will be doing, M1, right? And then we have M5, so this is M5, and this is M7, right? So again we have to look for pairs. So these are the 2 pairs. So as a result of those pairs, we will be getting AX plus B bar X, right? So this is also, we all know that here on this vertical axis I have taken A and A bar and A, right? So here I have taken B and X, right? So this is 0, 0, right? 0, 1, 1, 1, and 1, 0, right? So due to this, we have to take a jump, right? So similarly, we can do the same for the Y. For Y, we have 2. So this is 6, and this is 7. So as a result of this pair, we have AB, right? So now we got the simplified expressions, right? So if I write the minterms straight away, so how many terms I will be having? I will be having 1, 2, 3. 3 terms for A, right? So 3 terms for B, right? And 2 terms for Y. But after the K-map simplification, you can see that we have 2 terms for A and 2 terms for B, right? And 1 term for Y output. So this is the sort of simplification we have achieved after this K-map mapping, right? So now we have the state table, we have the simplification or simplified Boolean expression. So ultimately what we need to do next, we need to draw the circuitry, right? So here you can see that this is the combinational expression, this is the Boolean expression for combinational part, right? So, or this is the input to the flip-flop, and that is the combinational part, right? So here you can see AX, so this is A and this is X, right? So here we have A, right, AX, and for this we have BX, right? So I will be having AX plus BX. So this is the input, right? So that's what we talk or we take as the combinational part, right? So this is the input to the flip-flop or the storage element or the memory element. For this we have AX, right? And this is the B bar X, because here B is, so this is for, right, this is B bar and this is X, right? So B bar X I have already written, so AX plus B bar X, right? Okay, so for Y you can see we have A and B, right? So this is the circuitry, and you can verify after having 3 consecutive ones what we can have, right? So this is the circuit that can detect 3 consecutive ones, right? And we have started this on the basis of finite state machine design procedures, right? So next we have another problem, right? And that is we need to design a circuit that can check the parity, but here we have to mention, we have to specify what sort of parity, right? So whenever we talk about the data transmission, right, so there can be errors because we are sending ones and zeros, so due to some errors the ones can become zeros and zeros can be converted into ones, right? So as a result of that there will be, or there can be, errors. So in order to avoid those errors, we can have a very basic sort of phenomena or mechanism when we are sending very small data, right, a 4-bit number or maybe 8-bit number and so on and so forth, right? So we can use the parity checker, right? So what is a parity checker? Like, for example, if I have a number, 4-bit number, let me write down the number, for example A, right, and I have this number, 4-bit number, and what I have this bit, right, additional bit for the parity. So what I will do, I will count the total number of ones, right? If the number of ones are odd, right, so I will place a 0 here, right? If the number of ones are, for example, if A can be like this, right? So here for parity, what I have to do, I have to put a 1 in order to make the total number of ones odd, right? So this is the parity, right? So here we have to design a circuit that can check the odd parity, right? So the data stream, right, or the bit stream had odd number of ones, right? So here I've mentioned or explained that how we can make the number of ones odd. So here we have already the number of ones odd, so we have to place a 0 in at parity bit, right? So here we have even number of ones, so in order to make them odd we will be placing a 1, right? So this is the parity bit, and now the number of ones are odd, right? So what where to start, right? So first we can start from the even, thinking that the number of ones within the combination or within the bit stream, they are even, right? And input is 0 because the bits are coming, right? So if we have 0, next state obviously there is no 1, right? Additional bit, that is 1, so we will be at the same state, right? So here if we have 0, we are back on the same state, right? So even the output is 0, right? So even input is 1 even when we have input 1. So now we have to make a transition because now the number of ones are odd, right? So next state is odd, output is 0 over here, right? And then if we are at the present state and we applied 0, so the next state is odd, right? And we have the output 1 now because now the number of ones are odd, right? And then odd, right? And when we have an extra bit, that is 1, so now we are moved back to the even, right? And the output is 1, right? So after specification, right, what is next? We have to encode those states, right? So this is the symbolic representation, and now we have to represent those states by different symbols. So as we have only 2, right, possibilities, so we can use a single bit, right? So in the previous example we need 2 bits because we have 4 states, right, or 4 possibilities. So here present state 0, we have encoded even with 0 for the present state, right? 0, 1, 1. So this is the input, it will remain the same, and this is the next state, again even 0, odd 1, 1, right? So this is the same as we have in the symbolic table, right? So now what we have to do next, right? We have to calculate. So if I talk about the next state, right? So here if I talk about this column, because these are the inputs and this is the output, so 0 0 0 1 1 0 1 1, right? So I will be calculating the minterms for the next state, right? So if I mention the next state like this, right, ns, right? So here we have 2 ones, right? This is the present state and this is the let me call it PI, present input, right? So what I will be having, for this one present state, and this is not this is the dot, right? So PS, so this is 0, and for PI we have no complement, right? So plus for this one, right? So let me write down this M0, M1, M2, and this is M3, right? So we have for M1 we have PS complement because this is 0 and this is the PI input, right, dot, plus PS dot PI complement, right? So we have to remember that whenever we have a 0 at the position, so we have to complement it, right? So this is what? This is PS XORed with PI, right? So that is the Boolean expression for the next state, right? For the output, right? So we have what? Right? We have 2 ones, M2 and M3. For M2, what we will be doing, PS, right, plus dot PI, because this is complemented, right, and then plus PS dot pi, right? So what I can do, I can take ps as common, so pi complement plus pi, right? So this is what, this is 1 and we are left with only ps, right? So this is the, you can compute this from this encoded state table, right? So next we have, so ultimately what we need to do, we need a combinational circuitry that will be providing input, right, to this storage element or the flip-flop, and this is the output, right? So we have next state is equal to ps XORed with pi, and this is the output. And how we calculate it, so I have mentioned already over here, right? And if we talk about the circuitry, so you can see that ns, right, that is the next state, right, ps present state XORed with input pi, right? I mentioned the input as pi, right? And output, so here we have the output, and that is the ps, right, present state. So this circuit has the capability, right, for, or it can function as an odd parity checker, right? So you can verify. This is we have the timing diagram also, right? So you can verify yourself, right? So now we can also have two different type of machines, that is Melee and Moore machine, right? So in Melee machine, as we have already discussed, that output is dependent on current state and the input, right? Output is a function of current state and input, right? And in Moore machine, output is a function of current state only, right? So this is the key difference between these two types of machines, right? So next we have to talk about the vending machine, finite state machine, right? So we all know the functionality of the vending machine, right? So what we have the coin sensor, right? So obviously whenever we go to a vending machine, if we push a button in order to reset, or if there is some numbers that are being displayed on the digital display that we wish or we desire that those numbers has to be reset, so we push a button and all has been reset and we have to start from 0, right? So we want to buy a gum, right? So what is the requirement, right? So the package for the gum has been released after 15 cents has been deposited onto the vending machine, right? So we have a single slot for the coin, right? Dimes and nickels, right? And we have we can have no change, right? For example, after for example, from one state to another state, right? If for a particular time span you have not inserted, or you are not able to insert the coin, right? So there should be some mechanism, right? So that is there should not be any change, right? So this is the state diagram, right? So after, as I have mentioned, after going through or going over to a vending machine, right, we normally push a button in order to reset all values to 0, 0, right? So let's start from 0 cents, right? So here we have entered n, right? And if because we have two sort of coins, n is for, that is a coin for 5 cents, and then dime, that is the coin for 10 cents, right? So if you have inserted n, right, so you will move to the next state that is mentioning the 5 cent, right? If you have a dime, that is a coin for 10 cent, then you will move to the state that is representing that you are sitting at 10 cent position, right? So from here, from 5, what we need to do, we need to enter, or we need to insert a dime, right? Again, 5 plus 10, 15, right? And the machine will release the package, right? So if we are here at 10 cent, right? So will be entering or inserting a dime, n, right? Because n is for 5 cents, right? So here we will be move a transition from this state to this state, right? So here you can see that this column represents the present state and these are the inputs, right? So we can have both the coins, right? D and N, right? N is 5 cent and D is 10 cent, right? And there is a race condition, you can say, as we have race condition in flip-flops. So here in this vending machine we cannot insert 2 coins simultaneously, right? So this is not allowed, right? So you can see that we have no next state and no output when both are 1 1, right? So we are at 0. What is the possible scenarios? So we can insert, right, 5 cent, or here we have inserted 10 cents, right? So now if we are here at 5 cent, right, so you can see that we can insert 5 more, right? We will reach at 10, and here we have inserted a 1, right, dime, so we are at 15, right? So 1 1 here again not allowed, right? So we are at 10 cent, and when we insert 15 cents, right, and 5 cents, so we will be at 15 cent, right? And here if we insert 10 cents, right, and remember we are at 10, right? So this will, right, pass or surpass 15 cent and the package will be released, right? And normally we have the experience whenever we have the more currency that is inserted, so there is a box where we can get the remaining back, right? So if you don't have the coin for 5 cents, you can insert 2 coins of 10 cents and you will get back 5 cents and you will be able to snatch the gum package, right? So these are the states, and then we have the state diagram, right? And in this state, from this state diagram we have constructed the symbolic state table, right? So next what we need to do, right? So we have to encode those states 0 0, 0 1, 1 0 and 1 1, right? So if I go back, right, so I have mentioned 0 cents 0 0, 5 cents 0 1, and 10 cents 1 0, and 15 cents 1 1, right? And here we all know that D is right, 10 cents, and N is for 5 cents, right? So this is already set, right? And here again we have mentioned those different D's, right? D1, D0, right? So we have also encoded, right? So 0 0, because here we have the encoding, right? 0 cent, if I have to encode 0 cent, 5 cent, 1 0, right? And then 10 cent, 1 0, right? So this is the race condition, or this is not allowed, right? And then after encoding the state table, what we need to do next, we need to perform the simplification, right? So this is the K-map simplification. So we have the idea how we normally simplify, right? So first I will simplify for D1, right? So here you can see K-map for D1, and then I have to simplify for D0, right? So this is the simplification for D0, and after that I have to simplify for the output. So this is the output, right? So you can see that here we have the Dn, right? And here we have Q's, Q1, Q0, D and N, right? So Q1, Q0 and D and N, right? Right. So after simplification, what we can have, we will be having the simplified Boolean expressions, and finally we will be drawing the circuitry, and that is the circuitry for vending machine, right? So you can see that we have the N, right, and Q's, Q1, right, D, so D's, N's, Q's, right, and this is the flip-flop memory element that remembers the state, right? So you can think about that, how many cents are there, 5 cent, 10 cent, right? And then after 15 cents, having 15 cents, it will open or release the gum package, right? Okay, so next what we need to do, we need to design a circuit, right, or for this count sequence, right? So we have a very different count sequence, right? So we need to design, for example, if we want a count sequence like this. So normally we started from 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, right? So what normally we do, we start from 0, 0, 0, right, and finish till 1, 1, 1, right? So here we don't have any 1, 1, 1, right? So this is a sort of different. So after having this state, we will reset to 0, 0, 0. So this is something different, and we have to design a circuitry in order to have this complex count sequence, right? So first, if you are given that you have to design a circuitry that is providing this count sequence starting from 0, 0, 0, right, and after having 1, 1, 0, the circuit will reset to 0, 0, 0, right? So how we will represent? So we will present in the state transition diagram like this, right? So we will start from 0, 0, next state, and ultimately we will be resetting after 1, 1, 0, right? So from this state diagram, what we can have the state table, right? So here we have present state, next state, right? So if I go back 0, 0, 0, so this is very simple. Next state should be 0, 1, 0, 0, 0, 1, right? So here 0, 0, 1, right? So this is another some difference, right, from the normal counting, right? So let me mark the missing entities from the normal, right? So after 0, 0, 0, what we have 0, 0, 1, right? So and then we have 0, 1, 0, right? So after this, what normally we have 1, 0, 0, right? So 2 are missing. So you can see that 1, 2, and this is the third that is also missing. So let me mention again here, right? Right. So here you can see that 3 combinations are missing from the normal count, right? So what we are doing, right? So this is the present state and this is the next state, right? Present state and next state is don't care, right? So here present state, so I'll go back, right? So this is don't care. We declare this as don't care, right? So this is the present state and this is the next state, right? So here again 100 missing, so we declare this as don't care. So here again 111, and here again we have declared this don't care, right? So now what we can do, we can simplify, right? So here you can see that we have simplification for C plus, right? So plus, you can take it that this is this C for the next state, B for next state, right? A for next state, right? So here you can see we have to plot, right? 0, and this is don't care. So normally we map or plot the don't care, right? So right, so 1, right, and here again 1 and X, right, don't care. And here again we have to perform the same sort of mapping for B plus, right, and this is A plus, right? So you can see that we have A, C, B. So this is A on the vertical column, and this is in the row we have CB, right? So if I talk about, right, so for X 0 0 1, right, so you can see 0 B, right? So B has to come first, so this is the 0 1 actually, right? So for this one, right, so this is 0 1 1, right? So you can see that for this we have 0 1 1, right? So here we have to design a circuit that, right, can count a very different sequence, right? So here you can see that we have 0 0 0, right, and then we have 0 1 0, right? So what is missing in between, right? So let me write down. So here we are missing, right, 0 0 1, so that is missing. So 0 1 0, right, so 0 1 1, and then we are missing 1 0 0, right? So 1 0 1, 1 1 0, and here this is me. So those three combinations, they are missing, right? But what we need to do, we need to design a circuit that can count in this fashion, right? It will start from 0 0 0, so next state will be 0 1 0, and then next we will have 0 1 1, and then after skipping 1 0 0, we will be having 1 0 1, right, 1 1 0. So this is the problem statement, or you can say the specification, right? So what we will be doing, we will be drawing the state diagram, right? So we started from 0 0 0, right, 0 1 0, and then so 0 0 1 is missing. So after having this state diagram, right, what we can have, we can build or construct the transition table, state transition table, right? So you can see that we have 0 0 0, right, and the next, this is the next state, right? So 0 1 0, right, and 0 0 1, it's missing, and then because you can say that this is missing from here, and then 0 1 0, and next state is 0 1 1, right, and here 0 1 1, next state is 1 0 1, and 1 0 0, don't care because this is not present, right? So we have declared this as don't care, and 1 0 1, 1 1 0, next state, right, and 1 1 0 0 0. So this is also important, that after this combination we have to reset, make a reset, and here 1 1 1, right, don't care because this is not present here. So what we need to do, we need to simplify. We will be drawing the K map, right? So this is the K map for C plus, this is the K map for B plus. So plus mentions the next state for those corresponding variables, right? So after the simplification, right, So what we need, we will be choosing the flip-flop. So here we have chosen T flip-flop, right? So we know the truth table for T flip-flop, 0 0 no change, right? 0 1 1 1 0 1 1 1 0, right? So this is the excitation table. You can say we have the excitation table for the T flip-flop, right? So we will be filling the state table with those different possibilities, right? So and then what we can do, right? We can again simplify, but now we have the Boolean expressions, right? So this is the symbol for XOR, right? So here you can see we have TC A bar C plus A C bar, right? So A XORed with C. Similarly for TB we have A plus B bar plus C. For TA we have the A bar B C bar plus B bar C, right? So this is a simplification, right? And this is the circuitry, right? So you can see that here we have TC, right? So this is TC, and you can see TC is the XOR operation between A and C, right? So this is the XOR operation again, right? For TB, right? So we have A, B bar, and C. So they are ORed. So this is TB and this is TA, right? So A bar B C, right? B bar C, and they are ANDed. B bar and C is also ANDed, and they are ORed. So you can see we have A bar B C. So here we have TA, right? So this is the combinational circuitry we will be having at the input of those flip-flops, right? So here you can see that we have as we have make all the computations regarding or taking the T flip-flop. So here we are looking JK, right? So we have actually converted that JK into T flip-flop, right, by joining the two inputs, right? So by joining J and K we will be having the T flip-flop, right? So actually they are JK, but in fact they are now converted into T flip-flops, right? And they provide the same excitation and truth table, right? So this is the circuitry for counting this sequence, right? So that's all for today's lecture, right? So today we have studied finite state machine design procedures, right? And we talked about that how we can handle the state machines if we think about the computer system or computer hardware, right? And we talked about two different portions, that is control and the data path, right? So normally we have to we come across two main entities within the computer system, the control and the data path, right? So you can say if we have the data and obviously we have to manipulate the data, and in order to have manipulation or control over the that data, we need some sort of instructions, right, or control, or that is provided by the different states, right, different combinations of different states that the system is going through, right? For example, we have taken a very simple example of addition, right? Whenever we want to add two binary numbers, right? So first we have to load the data, and then for loading we have to send certain set of instructions that the data has been loaded, right? And after loading the data we have to send the instruction, right, to the logic units that now the data is ready for addition, right? So this is very simple example of how we manipulate, right, when we talk about or think about the computer a computer system, right? So data path, right, and the control, right? And then we have solved different examples on the basis of the finite state machine design procedures, right? So that's all. से अल्लाह हाफिज़, अपना ख्याल रखिएगा, अस्सलाम वालेकुम।